Okay, so now we're going to find shape function in 2D. So just like a shape function in 1D, a shape function in 2D has to equal a value of 1 at the node and a value of 0 at all other nodes. So let's start by drawing a plane. And this plane is going to have 4 lights, 1 on each corner. We're going to label these node 1, node 2, node 3, and node 4. Now we need to establish a coordinate system that we need to be consistent with. So typically to find a point in a 2D plane, you would use xy coordinates. But to find a point in this plane using shape functions, we're going to use zeta and eta. Messed that one up a little bit, but that is okay. So here's the origin in the center, 0, 0, and going this way is going to go to 1 zeta, and going this way is going to go to 1 eta. And so this will be -1, and that would also be -1. So let's start by deriving the shape function at node 3. You can start anywhere, but node 3 is kind of clean. So we're going to start with we know that there's going to be a zeta value, and we know there's going to be an eta value. Now let's put in the coordinates for node 3. Coordinate for node 3 is just 1, 1. So +1, +1. Now let's see what happens. We need this to have a value of 1, remember, to be a shape function. So let's plug in the coordinates for node 3 and see what happens. So we get 1 + 1 times 1 + 1. Well, unfortunately, that equals 4. This is 2, this is 2, 2 times 2 is 4. That needs to be 1. So to get to 1, we need to multiply this by 1/4, and that's going to get us to 1. So we need to add a 1/4 in front of this. And that very well may be our shape function for node 3. We need to double check though, but just make sure that it's 0 at one of these other nodes. We can go through this just logically. Since these are all being multiplied together, if one of these terms equals 0, all of the terms will equal 0. Since we're doing +1 and +1, we just need a -1 in either of these places. To get to n2, we would have to be negative eta, so that would make this term 0, which would 0 out the entire shape function. N1 is -1, -1, so definitely 0 there. And for node 4, we've got -1, and so that's also going to get us a 0. So this is definitively our shape function at node 3. Let's find our shape function at node 2. Shape function at node 2, let's start with a shape function that we know. We know there's going to be a 1/4 in there, but what we don't know right now is if it's going to be a positive or a -1/4. So the coordinates for node 2 is going to be 1, -1. So +1 and -1. Now when we plug in our coordinate for this, we end up with 1 + 1 times -1 - 1. This is going to get us a 2, and this is going to get us a -2. That gives us -4. So it does need to be a negative sign in front of the 1/4 to get us +1 for the shape function at node 2. Moving on to node 1. Let's go ahead and start with 1/4 again. We'll just do that every time. Okay. Let's plug in our coordinates at node 1, which is -1, -1. And let's plug in our values to check the shape function at node 1. So -1 - 1 and -1 - 1. -1 minus -1 is -2. This is another -2. -2 times -2 is +4. So that means we don't need to flip the sign of our 1/4. So that is the shape function for n1. Let's find the shape function for n4, our last one. I bet a lot of you could guess that that's going to be negative, but let's do the full derivation just to make sure. To get here, we needed to go -1, and to get up is just a +1. So let's check that, make sure that we get 1. So -1 - 1 and +1 + 1. -2, +2, multiply that together, gets us -4, so we need to have a -1/4. There are our shape functions and how to find them for a 2D plane. Pretty simple. The really powerful thing about this is, well, if you think about the shape of what this would be, the shape of the light, that's what we're finding with the shape function. If we only have one light on, it's going to be 10 or 1, a intensity of 1 at this point, and 0 at the other point. So it's going to look kind of like a like a Pringle chip almost, if it all comes down to 1 point. I can't draw in 3D very well, but it's going to be 0 here, 0, 0, and it will curve up to a maximum intensity there. Pretty simple. But what happens now if, say, we have an intensity of 0.5 at node 2, an intensity of 1 at node 1? Well, now we've got a weird combined shape function, because no longer do we just have 1 and then going down, sloping down to 0. We've got 1 and it combines with this intensity of 0.5 over here at node 2. So to do that's pretty simple. We only need to use 2 shape functions because we know that the shape function is 0, or 0 intensity, at 4 and 1. So we only need to use the shape functions that we derived from 2 and 3. So let's just put those down. So we're going to have the combined shape function is going to be 1/4 times zeta plus 1 times eta plus 1 plus shape function for n2 is -1/4 times zeta plus 1 times eta minus 1. Okay, so now where do we plug the intensities in at? Well, luckily we can just plug the intensities in right in front of the shape functions. This space right here, it's just a constant, so just add it in. So this would be 1 times all of this, and this would be 0.5, should left me a little bit more room, times all of that. And now we can plug in so this is the shape function for the combined with those intensities. And we can find the intensity of the light at any point in this 2D plane by just plugging in the values of zeta and eta where we want to evaluate. So let's say we want to evaluate some arbitrary place. Let's say at the coordinates, I don't know, 0.2 and -0.2, why not? So that would land us right around, we go up 0.2 and to the left 0.2, somewhere around here. We want to see what the light intensity is there, given that this is intensity of 1 and this is intensity of 0.5. And again, these are just arbitrary. They could be any value, any intensity that you want, or any pressure, or any heat. This can be used for all of that. So let's go ahead and plug in to our equation. 1 times 1/4 times 0.2 plus 1 times -0.2 plus 1 plus 0.5 times 1/4 times 0.2 plus 1 times -0.2 minus 1. And we can just throw that into a calculator. If I can get my calculator on the screen, still type this in. 1 times, I'll skip this part so you don't have to sit through it. Okay, welcome back. So I just threw this through my calculator and I actually made a mistake here, and I could have re-recorded the video and pretended like I didn't make the mistake, but I just think this is a really good reason to check your answer and see if it even makes sense. So that's how I caught this mistake. So let's go through my mistake that I made. When you're watching the video, I just put 1/4 here, not -1/4. So when I went through all of this, I ended up with -0.18. So I added 0.24 to -0.18, and I ended up with 0.06. That just didn't make any sense, right? Because we're looking at the light here. I've got an intensity of 1 here, intensity of 0.5 here. To get an intensity of 0.06, it needed to be somewhere like in this area or maybe this area. It just wasn't making a lot of, this area or this area. It just wasn't making a lot of sense. The second mistake that I made was I put 0.2 in for eta, I flipped my points. So my point that I calculated was actually over here, not over there. If you look for the eta value, the zeta value, I put 0.2, which is this direction, and then for the eta value, put -0.2, which is in this direction. So I said we're going to calculate here, we actually calculated here. So 2 mistakes that were only caught because this value just simply did not make any sense. How could the light be that basically 0 when we're here and we got light source here and here? So doing that made me look back through everything, and that's when I found my mistakes. And those mistakes were, this needed to be negative, and these were in the flipped positions. So recalculating for this point, we get a light intensity of 0.6. which is, you wouldn't have figured that out, right? It's actually more intense than the node, just node 2, but when you combine it with node 1, that's an action that makes sense. So that's how you derive shape functions and how you can use them to find the value for whatever you need at any point in a 2D plane.